Hi, this is my third time recording this. Excuse my voice, I'm getting over the cold still. I actually had blood drawn this morning over here for some allergy related stuff. Anyway, that's neither here nor there. Today, we're going to discuss function shifts and function stretches. Not even just functions, equation shifts and equation stretches. Meaning when you graph something and you want to shift it this way, or shift it up, or shift it down, or shift it to the left, or shift it to the right. Those are shifts. If you want to stretch it, whack, or stretch it, whack, or shrink it, shrink it. Those are stretches. And they're not hard at all. It's just four things to remember. Let's write them down. If you want to horizontally shift a graph by h being some number, like 3, you want to go 3 to the right. Everywhere you see an x, replace it with x minus 3. That's it. If you want to vertically shift something, like up or down, like up by 2 or down by 2, let's say k is 2. Everywhere you see a y, replace it with y minus 2 in that case. Y minus k. You want to go up by 2, replace y with y minus 2. Simple. How about stretches? If you want to horizontally stretch something by a factor of 2, for instance, if a, I'm going to say a right here, but it could be 2, it could be 5, whatever, then just everywhere you see an x, replace it with x over that number, x over a. In this case, x over 5 or x over 2 or whatever it is. Okay, that's it. You want to stretch it by a factor of 2, stretch things out by a factor of 2. Everywhere you see an x, replace it with x over 2. That's it. What about vertical stretches? If you want to vertically stretch something this way, like by a factor of 2, stretching it out, then everywhere you see a y, replace with y over whatever that number is. I say b, y over b. If it's by 2, y over 2. Just divide by the number you want to stretch by. If you want to shrink it by half, then divide by a half, in which case it's like multiplying by 2. But divide by half in that case. But usually stretching, not always. But anyway, that's it. If you want to shift, you subtract. If you want to stretch, you divide. Let's look at a bunch of examples. Suppose you have a question something like this. What is the equation of y equals x squared if the graph is shifted to the right 4 units? Pause the video, give it a shot yourself. In other words, how would this equation change if you shifted it to the right 4 units? What would the new equation be? All right. You want to shift to the right, horizontal shift. You want to go by 4 units. H is 4. Everywhere you see an x, replace it with x minus 4. So it was y equals x squared. Now it's going to become y equals x minus 4. That's an x minus 4 squared. You can multiply this out as well. It'd be x squared minus 8x plus 16. They would give you A, B, C, D, and E. They give you one that looks like this. X minus 4 squared, x plus 4 squared, x squared plus 4, x squared minus 4, who knows what else. They give you some other things, but on the ACT, that's roughly how it would be structured if they were to ask you something like this. Got it? Let's try another one. Suppose you have the equation y equals the absolute value of x minus 2. If the graph is shifted up by 3 units, what does the equation become? What's the new equation? Give it a shot. Pause the video. Resume when you're ready. Well, vertical shifts by k, every time you see a y, replace it with y minus k. We want to go up 3, so our k is 3. So we had y equals absolute value of x minus 2. This is going to become y minus 3 equals absolute value of x minus 2, which then you can get y by itself by adding 3 to both sides. So this becomes y equals absolute value of x minus 2 plus 3. Now, you probably learned in school that, hey, if you want to shift it up, you just add that up to the other side. That works out nicely when it's y equals something like you have a function here. You can say f of x equals this, where for any given x, there's always one y. But if you have something like a circle, it doesn't work so well. Where you can have, in a circle, for a given x value, like x equals, whatever, you could have 2 different y values. That doesn't work out so well. And there are a lot of things like this, circles and ellipses and, crazy stuff. So I like to think of it this way instead. Plus, this is more consistent. Just, if you want to do a horizontal shift, x becomes x minus h. Vertical shift, y becomes y minus k. Using different letters there, h, k, a, and b, because suppose we start mixing and matching like we're going to do in this next example, and you don't want to get confused. So let's try this one out, shall we? Okay, we have the equation y equals x squared plus 1. We want to shift it vertically 2 units and horizontally minus 2 units. In other words, up 2 and then to the left 2. Give it a shot. What would the new formula be? pause the video, resuming. Okay, here we go. Well, we have y equals x squared plus 1. Let's replace with the y's first. Vertical shift, we're going to have y minus 2 equals x squared plus 1. And if we want to do the horizontal one, y minus 2, every time we see an x, we're going to replace it with x minus a minus 2, which is x plus 2. And we can add 2 to both sides and end up with y equals x plus 2 squared plus 3. Kind of makes sense. If you're going up 2 units, then this becomes plus 3, and you want to move it back. You know, basically to get back to where you had it when x was 0 here, this needs to be a minus 2 plus 2. So that's the subtraction. I highly recommend you go out to Desmos' graphing calculator and play around with these there. Start to get a feel for it, why the minus is there. I mean, think about it logically. It has to be, because if you want to get back to 0, well then x has to be h. H minus h is 0. So if you want to shift it, that's why you're having to subtract. Same with stretching here. If you want to get, you know, if you're dividing by 1, you're right back where you were. But if you want it to be a factor of 2, well then, if this is 2, well then x has to be 2 to get back to where this was 1. 1 equals 2 over 2. So now all of a sudden x has to be, you know, twice as big for a horizontal stretch. You have to go out 2 places to get back where you were for the same y. And same thing for a vertical stretch. You know, for the same x, you know, you got to have y be, you know, b times that to be the same as it was. So y has to all of a sudden jump up to be where it was before, for the x. So the formula matches out. Go out to the graphing calculator, play around with it. You'll get a sense for it. And in the meantime, let's try a few more examples. All right, you have the equation y equals sine of x. We want to shift it horizontally pi units and then up 2 units. What's the new equation? Give it a shot. Well, again, we have y equals sine of x. Well, let's start messing here. Horizontally pi units. That means every time you see an x, you're going to replace it with x minus pi. And then up 2 units, every time you see a y, replace it with y minus 2. So now this becomes, if you add 2 to both sides, y equals sine of x minus pi plus 2. Starting to get the hang of this? Good. It's really not that bad. You do a bunch of these and they get to be pretty simple. Let's try one more on the shifts, then let's move the stretches. All right, suppose you have y equals cosine x minus 1 plus 2, and the graph is shifted down 2 units and to the left 1 unit. What's the new equation? Pause the video, resume when you're ready. All right, well, we have y equals cosine of x minus 1 plus 2. Let's see, we want to shift it down 2 units. Well, let's replace it with y minus a minus 2, because we're going down 2 units. Now we have a negative number, negative k here. So it's going to be y minus a minus. And then we have x to the left 1 unit. That's going to be a negative 1. So subtracting a negative 1. So that's going to be cosine of, that becomes x minus a minus 1, then the minus 1 over there, plus 2. This is x minus minus 1. This is minus minus 2. This is just y plus 2. And this is cosine x plus 1 minus 1. Hey, look at that. The plus 2's cancel. The plus 1 minus 1 cancels. This just becomes y equals cosine of x. It's kind of a reverse translation. You usually start out with something and make it more complicated. You could start out with something more complicated, bring it right back. Let me show you this example. You don't have to work it, but they could give you a kind of a pseudo trick question here. Because if you think about graphs, a lot of these kind of graphs, it's easy to tell what the shift is, but you can have some graphs where that's not the case. You can shift it and end up right back to where you were. A very basic example of that is with a line. Let's say you have a line going through the origin. Let's go with a very simple example of slope 1, y equals x. What happens if we shift this over by 1 and then up 1? You're right back where you started. Matter of fact, you could see it if we did that. To the right 1 and over 1, that means we're going to replace it with y minus 1 equals x minus 1. We're right back to y equals x. Because if you take this thing, this whole line right here, shift it over 1 and then up 1, you're right back to where you started. It's the same line. So they could confuse it with something like that. If they were to do something like that, they may do it with something like, y equals, 1/3 x plus 2. Then they do something where you're, shifting it around so you end up with the same thing. But that's usually, from what I've read, more of an SAT question. The SAT likes to have more trick questions like that. The ACT is more straightforward. Another reason I like the ACT more than the SAT. But just beware, especially for lines, that can happen. With other graphs you're used to, it's not as easy to do that. If you have a parabola, if you move it, it's going to be moved. You're not getting back to the same spot. Same with y equals x cubed. You move it, you're not getting back to the same spot. You could also do this with some of the trig functions. Sine, cosine, tangent, any of those, if you have, something like that, if you shift this over, you could end up right where you want, right where you were, if you just shift it over. Y equals sine of x is the same thing as y equals sine of, the graph at least the same as the y equals x plus 2 pi. Because the period is 2 pi. So you're right back to where you were. All right, let's move on to stretches. What's the equation of y equals x squared if you horizontally stretch it by a factor of 3? Go ahead and give it a shot. What would the new equation be? Well, horizontally stretching by a factor of 3 becomes, every time you see an x, just replace with x over 3. So if you have y equals x squared, that's a 2. This becomes y equals x over 3 squared, which is the same thing as x squared over 9, or 1/9 x squared. And they would give you a is 1x squared over 9, b is 9x squared, c is x squared plus 9, these kind of things. Or plus 3 or whatever, or times 3, I don't know. So that's how they would phrase it. That's all you got to do. You want to stretch it horizontally. When you think about it, x now has to be 3 where y was 1. If you had 1 here, 1 squared is 1. This now has to be, x has to be 3. To be 3 over 3, which is 1. To be right back to where you were. So let's do another one. What's the equation of y equals x squared if vertically stretched by a factor of 1/2? In other words, you have the parabola and then you're shrinking it by a factor of 1/2. So I guess it'd be shrinking by a factor of 2, but stretching by a factor of 1/2. So give it a shot. Pause the video, resume when you're ready. All right, it's a vertical stretch. B is 1/2. So every time you see a y, replace it with a y over 1/2. That equals x squared plus 1. Well, you can multiply both sides by 1/2. That's probably the easiest way to handle it. And you end up with y equals 1/2 times the whole other side. They could give you that, or they might give you x squared over 2, or 1/2 x squared plus 1/2. I don't know what they'd give you. But one of these, this would be A, B, C, D, and E, and this would be one of the answers, something like that. So let's try one more. What's the equation of x squared plus y squared equals 1, which is a circle, by the way, if vertically stretched by a factor of 2 and horizontally stretched by a factor of 3? Give it a shot. Okay, this is a circle of radius 1 centered at the origin. So all we're doing is stretching it vertically by a factor of 2 and horizontally by a factor of 3. So this is going to become an ellipse when we're done. So let's see. Vertically, we're starting out with x squared plus y squared equals 1. This is going to become, see, a vertical stretch by a factor of 2 means we replace y by y over 2. And every time we see a horizontal stretch 3, we're going to replace x with x over 3. They may call it quits right there and say that's x over 3 squared plus y over 2 squared equals 1. They may multiply things out to something like x squared over 9 plus y squared over 4 equals 1. They may multiply both sides by 36 and have this become 4x squared plus 9y squared equals 36. I don't know. It could be any of these things. And that would be, answer B out of, a bunch of different options, where you'd have x over 2 squared plus y over 3 squared equals 1, and 2x squared plus 3y squared equals 1, and who knows what else, but this is all there is to it. If you can remember this stuff, get used to working with it, that's all you're doing when it comes to shifts and stretches. Let's try one last one. Okay, here's a nice challenge for you. You have the standard equation for a circle centered at the origin. X squared plus y squared equals r squared, where r is the radius of the circle. Let's say we want to move it h units to the right. Don't know what h is, just h. And k units up. And it's stretched horizontally by a factor of a and vertically by a factor of b. What would be the equation of this new monstrosity we have? This new ellipse is really what it's going to be. Give it a shot, pause the video, resume when you're ready. All right. Well, let's see. We're starting out with x squared plus y squared equals r squared. We don't have to touch r squared. But let's see. If we're moving it h units to the right, let me make this for the x and this for the y. Let's see. H units to the right, every time we've seen x, replace with x minus h. K units up, y minus k. Stretched horizontally by a factor of a, divide that by a. Vertically by a factor of b, divide that by b. By the way, this is the generic formula for an ellipse. And that's all an ellipse is. Move it wherever you want, and then move it to hk, and it's a in the horizontal direction and b in the vertical direction. So if you have something like this right here, boop, that distance would be a. This distance right here would be b. So if you stretched it by a factor of 2, that would be 2. Stretch it this way by a factor of 3, that would be 3. If you moved it to HK, wherever the center is at HK. That's it. Pretty cool, huh? Ellipses aren't that bad, are they? Nah. Let's do one more. Let's say we have the equation x minus 3 squared plus y minus 2 squared equals 25. This is a circle centered at 3, 2 with a radius of 5. 5 squared is 25. If we move it 1 unit to the right and 2 units up, and it's stretched horizontally by a factor of 4, but vertically only by a factor of 2, what's the equation of the ellipse that comes out of this? Give it a try. Assumed you paused, unpaused. All right. Well, we're starting out with x minus 3 squared plus y minus 2 squared equals 25. We didn't change the radius at all. We could have, but we didn't. At least the original radius. Is weird when you start doing the shrinking and stretching thing. You keep the number over here, but the other numbers make it stretch. So anyway, let me just cordon off something here. And, all right, let me just make these guys. Let's see. A unit to the right. So that's going to be every time we see an x, we do an x minus 1 minus 3. And then we have 2 units up. So every time we see a y, we're going to y minus 2. Minus 2, because there's already a minus 2 there. And then we need to stretch it horizontally by a factor of 4. Horizontally by a factor of 4. And vertically by a factor of 2. So let's see. We have x minus 4 over 4. So that becomes x. I could do x minus 4 over 4. That becomes y minus 4 over 2. So x minus 4 over 4 squared plus y minus 4 over 2 squared equals 25. This is pretty much all there is to moving things around. Hopefully that clarifies a lot you've done in school and in preparation for the ACT. We're going to have one last video in this series, and it's going to be just on some miscellaneous things. things like translating periods of a sine function, and other just like 5 or 6 miscellaneous things. You're like, okay, you need to have this formula memorized to know how to use it. But this is it for this one. Go out to Desmos' graphing calculator. Play around with this. If you don't believe me on this, watch what happens. Plug both of these in. See what they look like. Good? Good? Good. All right, before we go, I just want to show you what we just did in Desmos. So we have our original equation here, x minus 3 squared plus y minus 2 squared equals 25. Let me copy this and make it over here. And let's actually put in the new one. So we translated it and we end up with x minus 4 over 4 squared. And then we ended up with y minus 4 over 2, I believe it was. And there we go. So does this look like the translation we expect? Is it moved over from a center? Is it moved over 1? Well, look at that. The center here is along this line of 4 when it was at 3. And it's moved up 2? Well, it was a center line here at 2. Now it's moved up here to 4. So yeah, it's moved up. The center of the ellipse is now moved over 1 and up 2. And has it stretched properly? Is it stretched by a factor of 2 in the y direction? Yeah, it looks about like that. And is it stretched by a factor of 4 in the x direction? Yeah. So I recommend you double checking your work out here in Desmos. See if it, looks like what you expected it to look like. So for instance, if we did that, okay, that would not be what we expected. We expected to only be stretched by a factor of 2 in the y direction, not by a factor of 4. So there's all kinds of fun things you can do here. You can go in and, what if we only did this? And let's go back to what if it were only for the original and then like this. So if it were centered at the origin originally, well, is this moved over by a factor of 1? Yeah. Look at that. Is it moved up by a factor of 2? Yeah. Looks like the center line on the ellipse is up 2. And is it stretched by a factor of 2? Well, it was a radius of 5. Now, if you start at 2 here, it goes up to 12. Well, 12 minus 2 is 10. That makes sense. And is it stretched by a factor of 4 the other way? Look at that. It goes all the way out here to 20 instead of 5. Yeah. So anyway, it's a good thing, a good idea to go out here and actually test out things. And let me show you something else we can do here. Let's say you had something like this. F of x equals, something simple. X squared. Okay? Check this out. You can make g of x equal to f of x. But you can also do something like, well, let's do x minus h. Okay? Now let's add a slider for h. So we added the slider for h here. What happens if we go in the positive direction? Look at that. X minus 4 moves the parabola over to the right 4. If we go in the negative direction, it goes negative. So x minus a minus 5, which is x plus 5, goes over here to the minus 5. So anyway, you can do all kinds of fun things like this out here to kind of get the hang of it, to see how things actually work. It may help your intuition. Anyway, I just want to show you this and hope it helps.